Okay, here we go again. In this problem here, we want to solve this integral of square root of 16 minus x squared. However, they're giving us the hint to use geometry. So if we're using geometry, we want to just start off with a right triangle here. And then we want to see how this here is defined as a right triangle. So we're going to have our Pythagorean theorem, a squared plus b squared is equal to c squared. And we're just going to arbitrarily solve for one of these variables to see if we can set it up in that fashion. So we have a squared is equal to c squared minus b squared. Then we can solve for a. So a is equal to the square root of c squared minus b squared. Now we look at our integral. Well, this is essentially the same thing as saying 16 minus x squared. So we can say if a is equal to the square root of 16 minus x squared, then we can also say c squared is equal to 16. And we can say that x squared is equal to, we can say b squared is equal to x squared. So now we have this set up here on the right for our right triangle. What we can do here is define any part to be really a or b, and of course the hypotenuse needs to be c. So we have c is equal to 4 now, because 4 squared is the same thing as 16. We can either let the base be b, or we can let it be a. So depending on how we set up this triangle, all it does is just says in our integration from 4 to 0 to the square root of 16 minus x squared dx, it just sets it up as either a cosine statement, a cosine square statement, or a sine square statement. So I'm going to set it up in a fashion where I'm going to have a is the base. So a is equal to the square root of 16 minus x squared. And I'm just going to let the height here, or b value, is equal to x. Okay, so then now I want to use sine and cosine somehow. So I'm just going to pick this angle here, the lower right angle here, and I'm going to call that theta. So when I'm saying if that's theta, that means I can do a few setups. For my sine statement then, if I say sine of theta, well, that's the opposite, which in this case x, over our hypotenuse, which in this case is 4. So we can solve for x so that we have a nice value for our height. So if I solve for x, I have 4 times the sine of theta is equal to x. So this tells me I have x is equal to 4 sine of theta. Okay, so this is a very important equation that we're going to need. So we're going to box that for now. And then the next one we're going to do is we're going to solve this for cosine. So I'm going to have cosine of theta is equal to, well, the adjacent side in this case is the square root of 16 minus x squared over our hypotenuse, which is 4. So, and then in this statement now, I'm going to solve for square root of 16 minus x, because that's exactly the integral we want. So this is now saying we have 4 times the cosine of theta is equal to the square root of 16 minus x squared. So this is great news. So this is our second equation. We're going to substitute this statement into our integral. And then we have a statement with sine and cosine, or specifically with cosine. So we have a new integral now. So we're taking the integral from 0 to 4. But instead of the square root of 16 minus x squared, that's the same thing as 4 times the cosine of theta dx. Okay. So far this is pretty good. However, we have our statement in data, but we are integrating with respect to dx. So we need to rewrite dx somehow as d data. So in order to do this, we're going to use our sine statement because we have x is equal to 4 sine of x. If we took the derivative of this, then we're going to have a dx statement. So if I took the derivative to the left, that would be dx as equal to, well, the derivative of 4 sine of theta. Well, that's just 4 cosine of theta, d theta. Which is great news. So now I can take the statement here, and which is dx for cosine d theta, and substitute it into my new integral. So I will have a statement that's just with theta and d theta. So let's do that substitution now. I have the integration from 0 to 4 of 4 cosine of theta, but I'm going to have, instead of dx, this is times 4 cosine of theta d theta. So we're almost there to be able to start integrating this. However, since we're switching the statements to everything with data now, and no longer x values, our boundary values needs to be changed. So we're going to have new boundary values for 0 and 4. So in order to figure out these new boundary values, well, these were our old x values. This used to be x equals 0, and this other one used to be x equals 4. So what we're going to do is take one of the equations we have that dealt with x. And an easy one to do is this brown one that we've used, that is x equals 4 sine of theta. So I'm going to retake that one and then substitute in the values of x. So I'm going to need x is equal to 4 sine of theta. And I'm going to substitute in our two values of x. So first, we have our x value is equal to 0. So then if I have 0 is equal to 4 sine of theta, then my job here is to solve for theta. I'm going to divide both sides by 4. So I have 0 over 4 is equal to sine of theta. And so sine of theta is equal to 0. However, we still got to take the inverse to both sides. So theta is now equal to sine inverse of 0. So we have a theta and a sine inverse. So this will give us an angle value. And then we use our fancy unit circles, and we can, or we just quickly punch into a calculator because we're taking the sine inverse of 0, and that will give us 0. So now we have theta is equal to 0. Okay. So this gives us one of our boundary values, our lower boundary values. So this is our new a value. Now we need to use what happens if x is 4, which is the original b value. Then we're going to say, okay, we have 4 is equal to 4 sine of theta. And we divide both sides by 4. So we get 1 is equal to sine of theta. Oh, this is starting to look very nice, because then theta is equal to sine inverse of 1, which tells us that theta is now pi over 2. So this is great news. This tells us that this is our new b value. Okay, so this is great. Now we have two new boundaries with respect to theta. So that now when we look at our integration here, we can put in these new boundary values and we don't have to worry about any backward substitution. So I'm just going to grab this statement here, and I'm going to substitute in our new boundary values. So instead of 0, oh, in this case, we still get 0. But instead of 4, our new b value here is actually pi over 2. So I'm going to just rewrite the statement here. I have the integration from 0 to pi over 2 now. And I'm going to clean up some of this algebra in the middle here. I now have 16 cosine squared of theta d theta. So we're almost done with this problem. The problem here now is that we can't just integrate sine squared of theta. The reverse power rule doesn't work. So just to remind us, what is the reverse product rule, I should say. The reverse product rule really states that, hey, if you have the integration of x to the n dx, this is equal to x to the power of n plus 1 all over n plus 1 plus c. So this statement doesn't work because we are dealing with trig values now. So what we have to do here is somehow rewrite the statement. Instead of saying cosine to some power, we need some trig value to the first power. So in order to reduce these degrees here, we're going to first start with the Pythagorean identity. This gives us sine squared of theta plus cosine squared of theta is equal to 1. However, any way we solve or substitute any one of these values in doesn't actually help us. So now we need a second equation. So our second equation is a double angle formula for cosine. So I have cosine of 2 theta is equal to sine of theta. Oh, no. So we got to be careful here, right? The rule really says it's cosine squared of theta minus sine squared of theta. So we got to be very, very careful here on remembering the setup, okay? If we kind of secretly forget the setup, we just quickly, Google search it. So with these two equations, we're going to combine them together, and we're going to be able to substitute in cosine squared of theta in, and then we'll have a statement with no more powers. So what I'm first going to do is get rid of the sine in our double angle formula. So sine squared of theta is equal to negative cosine squared of theta plus 1. So then I can do the substitution now. So I have cosine of 2 theta is equal to cosine squared of theta, and then it's going to be minus. So I have to be very, very careful with this minus here. So I'm draw a little parentheses so we understand I've got to do some distribution later. Minus the cosine squared of theta plus 1. Then we have cosine of 2 theta is equal to cosine squared of theta. Now we're distributing this negative here, and be super careful. This gives us positive cosine squared of theta minus 1. Oh, this is starting to look really good, actually. So this gives us the cosine of 2 theta equals to 2 cosine squared of theta minus 1. Then let's solve for cosine squared. So this gives us cosine of 2 theta plus 1 is equal to 2 cosine squared of theta. And so in the end, we now have cosine squared of theta is equal to cosine of 2 theta over 2 plus 1/2. Like, whew, this is great. We finally have a statement using cosine, but we now don't have to worry about any powers, because the powers are actually the things that give us a lot of trouble. So looks like I'm running out a little bit out of space. Let me resize this problem here so I can fit everything. Okay. And then so I'm gonna copy this here. I'm gonna bring it down so that we can now do some of our substitutions. So we have the integral from 0 to pi over 2 of 16. I'm drawing parentheses here because we're going to do a substitution, and then we have of d theta. In this substitution here, I have cosine of 2 theta all over 2 plus 1/2. Okay, so I'm going to do some moving some factors around so that I can clean this up just a little bit. So it looks like I'm running out of space, so I'm going to just copy the statement. I'm going to slide over here. Here we go. So I'm going to just keep going down, actually. Ta-da! Okay, great. So I'm going to do some algebra cleaning up. Okay, I can either distribute the 16 in, or I can factor out the 16. It really doesn't matter. So for the time being, I'm just going to factor out the 16. So this is 16. Okay, and then I'm going to take the integration of each individual terms. So I'll take the integration from 0 to pi over 2 of our cosine of 2 theta all over 2 d theta. And then I'm going to also take the integration of 0 to pi over 2 of 1/2 d theta. So for our propal statement here, where we have cosine of 2 theta, this is just a very, very quick u substitution. So all I'm just trying to say is, okay, I have u equals 2 theta. That means du is equal to 2d theta. And then, so that just gives us du over 2 is equal to d theta. So I can just do this one integration here using a quick u substitution. So secretly, I still have the 16 on the outside. I'm going to rewrite the statement using the u substitution. So I still have the integration from 0 to pi over 2. I have a quick u substitution. Okay. I'm going to get our cosine. But inside here, I write u is still over 2. And then instead of d theta, this is now going to be du over 2. Okay. So here, I'm not going to necessarily bother changing these boundary values again, because I'm secretly going to backward substitute for this situation. I don't want to necessarily just take that process here. So I'm just going to finish this single term first, and then I'll go back and deal with the other term later. So I have to be very, very careful that this 16 here is implied to my 2 separate terms, okay? So I'll be very, very careful there. It's like that. Okay. So now if I do this statement, well, the antiderivative or the integral of cosine of u, well, that's just sine. So that's great. I'm going to now have the sine, okay, of u, but u is 2 theta. So I'm going to rewrite this as 2 theta. And then I have the 16 still multiplied on the outside, but in the bottom here is over 4. And so, yeah, that's great. That's exactly what we want. Okay. I've left all this extra space here for the second term. So I'm going to scroll back up and do our second term. Well, our second term here is actually very, very nice and easy to do because it's just the integration of a constant. And if that's the case, it's just whatever that, it's just going to be our data value. So this is super easy here. This is just going to be 1/2 of data from our boundary values of 0 to pi over 2. So we can kind of bring all this stuff together, okay? We have the single term statement right there, okay, that we're going to add, okay? All right, we're going to just bring this down. We're going to kind of bring this all down, kind of right there. And then we're going to add to this green sine of 2 data statement, but I have to make sure our boundary values for this as well, okay? So our boundary values here is just from 0 to pi over 2. There we go. Let me clean this up real quick. Just look a little bit nicer. There we go. Okay, great. And then from here on, it's just some straight up algebra work. So there's nothing too fancy here. We just have to remember we have to distribute the 16 to everything and then take each individual boundary values. And then after that, we're more or less done. So let's just do that really quickly. I'm still going to leave the 16 on the outside and multiply that later, okay? So I don't have to worry about zeros, right? Zero is just 0. So sorry, the sign of 0 is just 0. I just really have to worry about our pi over 2. So I have sine of 2 times our pi over 2 all over 4. And then I have to add this statement over here. Well, again, the data of 0 is still 0. And then I have pi over 2 inside data. So the only one I have to worry about, again, is the pi over 2. So this have 1/2 of pi over 2. Okay. Let me try to be consistent with my colors here. Sorry about this. Let me just quickly adjust my colors, I'm using this light orange color here for my pi over 2. Okay, so let's look at the green statement here. So the sine of 2 times pi over 2, well, that's just sine of pi. Okay, so the sine of pi is actually 0. So this whole statement here is actually 0, which is great. It just makes our life a little bit easier. So now on the outside I have 16 times 0 plus, well, I have 1/2 times pi over 2. So this is just going to be pi over 4. Okay. Our giant brackets on the outside, and then, oh, cool. So then all this says is I have 16 times pi over 4. That's great news. So that's just 16 over pi over 4. And then our final answer is just 4 pi. And there you go. We're all done. Huzzah! And that'll be it.